Okay, so we will see an application of open mapping theorem. So the one which we are going to prove today is called the inverse function theorem. Okay, so it's called inverse function theorem. Okay, so what is inverse function theorem for us? So let us try to recall the inverse function theorem on R first. Okay, so on R, what was the version of inverse function theorem that you had seen? So the version, if you can, anybody recall what was inverse function theorem? For example, functions which are differentiable in R. Do you remember? Okay, so fine. If you don't remember, I'll record it for you. So here, the statement is: suppose I have f inverse dash equals to 1 upon f of x. Yeah. So yeah, I need certain condition on f. So f I'm taking to be continuously differentiable. Okay, so that's a C1 function with non-zero derivative at a point. Okay, non-zero derivative. Let's say at a. Then what I can say, then f is invertible in a neighborhood of a. Okay, so if I have a function which is C1 function with non-zero derivative at a point a, then my function is invertible in a neighborhood of a. Okay, so moreover, moreover, the inverse is continuously differentiable, and derivative of f inverse, it is given at b equal to f of a, is given by, that just follows from uh, chain rule. So f inverse prime and p is 1 upon f of a. Okay, so you really need to take this f to be non-vanishing at a. Okay, sorry, this is f prime of a. Yes, sir, f prime of. Yeah. Okay, so this is, as I said, it comes directly from this relation. You anyway get it from chain rule. Fine. So now, if you, in place of here, I am taking function defined on R, let's say some subsets of R, and real valued function, and you can even have functions of several variable, and then this condition of non-vanishing derivative needs to be replaced by non-vanishing of determinant of the Jacobian. Okay, so if you have seen several variable calculus, you will probably get a statement like that. Okay, so now you see this non-zero derivative is to ensure that the function is locally injective. Yeah, because if of course here I am saying that the derivative is continuous, and if it is non-zero at a point a, then in a neighborhood of that point a, the function will f prime, since it is continuous, it will also be non-zero. And now on that neighborhood, the function is going to be injective, because if you take any 2 point whose functional value are equal in that neighborhood, then by means of mean value theorem, you will get a zero of the derivative between those 2 points, right? So therefore, actually, this non-vanishing is to ensure that your function becomes locally injective. Okay, so that is what you have. And anyway, so now that you know this, what is the statement over R, we are going to now state the inverse function theorem for holomorphic function. Okay, so inverse function theorem for holomorphic functions. Okay, so what do I have over here? The statement is as follows. So let V be a domain, let V be a domain, and f belongs to h of B, so that means it's a holomorphic function on V. Suppose f is injective. Suppose f is injective. Denote u equal to f of V. Then f inverse from u to V is also holomorphic, and this will give me that f inverse prime at w is equal to 1 upon f prime of z, where w is equal to f of z. Okay, so exactly the same statement. Okay, here I am assuming that I'm taking my function to be injective itself. Okay, because you see I don't have that way mean value theorem over here, because in R I could assume that the derivative is non-zero, and I could say that the function is going to be injective. But here, since I don't have mean value theorem, so I'm assuming that my function is going to be, my function is going to be injective. That is what I'm asking for. Okay, so here, of course, I am going to, uh, apply one statement which I believe I had, stated at the time of proving holomorphicity of branch of logarithm. Okay, so what was that statement? You can recall this one. Um, okay, so what was the statement? The statement was um, as follows. Okay, so the theorem was that let U be open subsets of C, and I think, and let's say G1 from U to C and G2 from V to C be continuous functions such that G1 of U is subset of V and G2 composed G1 of Z is equal to Z for all Z in U. If G2 is differentiable and G2 prime does not vanish on V1, then G1 is holomorphic on, sorry, this is, doesn't, there is no V1, is G1, yeah, G2 prime does not vanish on V, then what do we have? Then we have G1 is holomorphic on U, and this G1 prime of Z was 1 upon G2 prime of G1Z. So that was the statement which I had proved when we were talking about holomorphicity for branch of logarithm. Okay. Now this statement can be, readily applied to get the proof of inverse function theorem. Only thing that you really need here is that here I need my function to be non-vanishing. Okay, so that is what is not given here. Okay, so we really need the condition that the function is non-vanishing. Okay, so I was given, like you saw here in the hypothesis, there is a slight difference here. I had assumed that the derivative, non-zero derivative at a, but here I did not assume that. I just assumed f to be injective. Okay, so that's the minimum requirement to say something is some function is invertible. So I just took that one as hypothesis, and now if I want to apply this particular theorem, what I really need is to make sure that my function is actually going to be, non-vanishing. Okay, so is this clear to all of you?
Yes, sir.
Yeah, so if I want to really apply this particular statement, what I effectively need is that we need our function to have non-vanishing derivative, because as once that is there, every other thing is already there, so this f inverse will make sense. Of course, it's going to be continuous, so I can show continuity by using open map. So f inverse will be continuous, so everything will come in place, except for the fact that I need to apply this particular result. I need to make sure that my function, the derivative, is non-vanishing, whereas I only have my f to be injective. Okay, so proof. So this theorem I have already proved. I am not proving that. So proof of inverse function theorem. So to use the above theorem in our proof, we first show that f prime f is injective implies f prime does not vanish. Okay, so now here I am writing a statement which you need to be really careful working with. Okay, so here I have f is injective in that open set, so that I am from there I want to say that f prime does not vanish. Now you need to be careful. Why? So here, dangerous bend, this statement, like this last, the claim that I have made is not true in R, for example. So really in R, I needed to take that my derivative is non-zero. So this statement is not true in R. Why? For example, take fx equal to x cubed. So this function is an injective function, but its derivative is vanishing at x equal to 0, for instance, right? Yeah, is this
Yes.
clear to all of you? So you really
Yes,
need
sir.
careful that we are actually going to have this complex analytic thing going on over here. So really, this is a particular property of complex holomorphic functions. Okay, so I'm going to show here that if I have an injective function, then the derivative does not vanish. Okay, so now this particular aspect is often proved using Rushi's theorem, and which we have not yet learned. So it will come later when we are going to talk about singularities and other stuff. So at that time we will learn about Rushi's theorem, but so far we do not know what is Rushi's theorem. So I'm going to give a proof which will avoid this Rushi's theorem. Okay, so the first step is to prove that the derivative is non-vanishing. Okay, and then we also need to show that all these uh, functions are continuous and all of that, but that will be taken care of clearly, because since my function is given to be injective, so my function will be non-constant, and therefore my function will be open map, the function will be an open map, and therefore the inverse will be continuous. So the continuity part, so this continuity part will be automatic. So G1, G2 will be automatically continuous. Of course, here your G2 is F. Okay, so and G1 is your F inverse. So continuity will come automatically, but the non-vanishing of the derivative is what we need to ensure. So we are going to therefore prove the non-vanishing now. Okay, so we prove it by contradiction. So we prove by contradiction. Okay, so let us see if we can uh, get through this. Okay, so let uh, I have to do what? I have to show that the derivative does not vanish, right? So I'm going to assume that, so let f prime of a equal to 0 for some a belonging to, I have my f, domain of f is v, right? So for some a in v. So I'm taking a point from v where the derivative is vanishing and I need to get a contradiction. Fine, all right. Now, of course, my function is given to be holomorphic. So what I do is that I write down the power series expansion. Okay, so we write f of z is equal to, let's say, a naught plus a1 into z minus a plus a2 into z minus a squared and so on and so forth. So we write a power series expansion of f around a. Okay, and of course here we know that these constants can be given in terms of the derivative. So ak is the kth derivative of f at a divided by k factorial for k bigger than or equal to 0. Right? We know this. All of you agree to that?
Yes, sir.
Yes, sir.
Now, suppose, so from here, what do I know? I know, for example, a naught is f of a, and a1 is f prime of a, and f prime of a we have assumed it to be 0, so a1 is equal to 0. Okay, so therefore, clearly after a naught, I know that at least one derivative of the function at a is 0. Okay, so what I am going to do, I am going to collect all the possible uh, uh, case for which fk of a is 0. Like I will kind of uh, take all possible such derivatives where a is a 0 of those functions. Okay, so let k is strictly bigger than 1 be such that ak is not equal to 0 and a1 so on and so forth ak minus 1 is equal to 0. Okay, so for example, if your a2 is not equal to 0, then your k is just 2. Okay, but if your a1 a2 both are equal to 0 but a3 is not equal to 0, then your k is 3. Okay, so after a1 you go and look for the first coefficient where you get non-zero, first k where you get non-zero coefficient. So if my k is like this, then how does my function look like? So then f of z looks like a naught plus ak z minus a, sorry, what is a naught plus ak z minus a power k plus so on and so forth. Okay, so or like I can write one more term, ak plus 1 z minus a power k plus k plus 1, which is plus dot dot. Okay, so this is what we get. All of us agree to this? Yeah, that's how my function
Yes,
look
sir.
like, right? Okay, now what I can do, I can just write it as a naught plus ak, sorry, not ak, but z minus a power k. I can take it common, and then I write ak plus ak plus 1 into z minus a, and so on and so forth. Okay. So I write it like this. So therefore, I call it a naught plus z minus a power k into gz. Okay. Of course, gz is also going to be a holomorphic function because it is given in terms of a convergent power series. Okay, so this is a holomorphic function, means where gz is, as I wrote, summation n bigger than or equal to 0, ak plus n z minus a power n. So that's my G, and this is going to be holomorphic in a neighborhood of A. Okay, because the power series of f and the power series of g, they have the same radius of convergence. Okay, I'm not writing so explicitly, but you already know these kind of things. Same radius of convergence as f around a. So whatever the radius of convergence that we got of f around a, the same radius of convergence we are going to get. So therefore, this is going to define a holomorphic function in a neighborhood. Fine, all that is good. Now, moreover, I have what? I have ak is not equal to 0. Since ak is not equal to 0, we get that g of a is not equal to 0. Fine, that's okay. So now what do I do? I have this. So what I am going to do is that, so g is a non-vanishing function at a. So what we can do is that we can figure out a neighborhood where the function is going to be non-vanishing. Okay, so we can find a neighborhood, let's say b a epsilon, such that g is non-vanishing there. Okay, so I get a neighborhood where my function g, because g at a is not equal to 0, so in a neighborhood around a, function will be non-zero just by continuity. So I get this one. Okay, so g is non-vanishing, and once g is non-vanishing, what we are going to do is that we are going to take kth root of this g. Okay, so my claim is that, so there exists a holomorphic function h on b a epsilon such that h power k is equal to, sorry, is equal to g. Okay, so basically I am taking kth root of g. Okay, so this was in one of the problem sheet problems. So like if you have non-vanishing function, then you can, for example, take square root, cube root, and so on and so forth. So here I am taking the kth root. Okay, so if you really need the concrete function, I can take the concrete function. Okay, so this exists. Let me write also for you. This exists using branch of logarithm. So branch of logarithm of g. So g is a non-vanishing function. So I can take branch of logarithm for g. So that is one takes h equal to, like for example, if you want, you can take h equal to exponential of log of gz and divided by k. Okay, so you can take this one, and that is what is your h function, and some log is some appropriate branch of, like log is some appropriate branch of logarithm defined on, so here log is defined on g of b a epsilon. So whatever branch you like to choose, anyway this set on b a epsilon g is non-zero, so this is staying away from 0, so we take some branch of logarithm. Okay, there. So therefore what I get effectively, why did I take the square root? The square, or the kth root, I took because then if I have this, then I can write h of z is equal to a naught plus, I already had z minus a power k over there, so this is z minus a times h whole power k. Okay, so this is how I can write. Okay, all good. So this is what I get. Now let us observe the following. This particular function, this function, so note the function z minus a times h. This function has a 0. What is the 0? 0 is at z equal to a, right?
Yes.
Right?
Yes.
Because, for example, means I'm treating at this moment this as a whole. Okay, but anyway, this has, sorry, just a moment. Yeah. So I want to have this. Yes, so this is f at a is a naught. Yes, so this, note that this function vanishes. Of course, h is anyway a holomorphic function, vanishes at z equal to a. Okay, so therefore what happens is that if I look at the image of b a epsilon under of means image of this function, so if we look at the image of b a epsilon under this map z minus a into h, then uh, 0, then um, this is an open set containing 0. Okay, so what I get is that this, when I think of this function, this is going to be, of course, h is a holomorphic function, so z minus a times h. This is going to be a non-constant function, and it vanishes at z equal to a. So when you look at image of an open set under this holomorphic map, that's going to be an open set, and this open set contains 0. Okay, so therefore, if it contains 0, that means what? If it contains 0, that means there will be a ball around 0 which will be contained in the image. Okay, so is an open set containing 0, and hence containing a ball b0 delta, let's say, for some delta positive. All of you agree to this?
Yes.
Okay, so my image is an open set which contains this ball b0 delta. It contains 0, so image is an open set, we know by open mapping theorem. So therefore it contains an open ball, so I can write by open mapping theorem. Okay, very good. So what do I do with this ball? So with this ball, what I am going to do is that I am going to generate a contradiction. How? So notice, see, this is in the image, right? So anything that I take from this ball, I will have a pre-image for those points, right? For z minus a times h. Is it clear what I'm trying to say?
Yes, sir.
Any point that I take, for that I am going to get a pre-image. Okay, and remember here I am going to use k is bigger than 1 at a very subtle point. So for every point in this ball I am going to get a pre-image. So what are the points that I am going to take? So choose pre-image of the points delta by 2, that's number 1, and followed by delta by 2 times e power 2 pi I divided by k. Okay, remember k is strictly bigger than 1, so therefore these two are different numbers. Clear?
Yes, sir.
Yeah, so these two are different numbers, and I can choose p-image. So say z1 minus a times h of z1 is delta by 2, and z2 minus a into h of z2 at delta by is equal to delta by 2 e power 2 pi I by k. Okay, so these are two distinct points, like distinct as k is strictly bigger than 1. Okay, so that's important. So I get these 2 points, which are, one is p image of delta by 2, another is p image of delta by 2 e to the power 2 pi I divided by k. Okay, so essentially that's of the same modulus delta by 2, but it's not same as delta by 2. I am just multiplying some kth root of unity. Okay, so if that happens, then what do I get? What is, can you tell me what is f of z1? Tell me what is f of z1? F of z1 is, remember, this is a naught plus z1 minus a into h of z1 whole power k. So that is a naught plus delta by 2 power k. Agreed?
Yes. Yes, sir.
What is f of z2?
Delta by 2 e to a naught plus delta by 2 e to the power 2 pi I by k to the power k.
So effectively what?
Delta by 2 to the
Delta
power
by 2
k.
to the power k.
Same exactly.
Same, exactly the same. That is my point. So sorry, this is z2 power k. So this is also a naught plus delta by 2 whole power k. Because I had taken, a kth root of unity. So when I take the power k, that becomes 1. So effectively I'm getting the two different. So now these 2 points are, so note z1 is not equal to z2, right? All of you agree to that? Because these two numbers are different. So therefore, clearly their pre-image cannot be the same. So the pre-image z1 and z2 are not equal. And I get f of z1 and f of z2, they are of the same value. So that implies what?
F is not injective.
Not injective.
Not injective. And what was the hypothesis?
F
The
is injective.
The hypothesis was f is injective. So therefore, I get a contradiction. And why did I get a contradiction? Because I started by assuming that f prime is equal to 0. Right? Is it
Yes,
clear?
sir.
Yes, sir.
So this is a contradiction. Great. So therefore, I get a contradiction. So that means I am done proving that f prime is non-vanishing. So we get f prime is non-vanishing. Moreover, as f is an open map, so f inverse is continuous. So that implies by theorem we get inverse function theorem. Okay, so I had really taken a minimal hypothesis, namely the function being injective, and then I showed that I am going to have, I will actually have this thing that my means I'm taking an injective function, then I'll get derivative to be non-vanishing, and then I'll get this inverse function theorem using this particular one, more general theorem which we had. But of course there we had a lot of hypotheses, namely this assumption of when non-vanishing of derivative and all that, everything was there. Okay, so we really have inverse function theorem, means in the fullest capacity. Okay, now you can for example you can see that why this same argument does not work. For example, in R, it does not work in R for a very simple reason. For a simple reason that, for example, if my key is odd on R, you are not going to have any, kth root of unity which is other than 1. If k is odd, then on R you are not going to get a different kth root of unity other than 1, isn't it? So here effectively I
Yes,
got
sir.
the contradiction by using the fact that once k is bigger than 1, I will be able to find out a primitive root of a root of unity which is different from 1. Okay, so here I had delta times 1 and delta by 2 times 1, and here I had delta by 2 times some other uh, kth root of unity. But if for example k is odd, then on for example point like on R I cannot find a different kth root of unity. Okay, so precisely you see the counter example that I gave, the x cube for in case of R, that's of degree 3. Okay, so clearly you see there is a lot of important uh, things about complex numbers, and that really plays a role to get these kind of special properties of complex holomorphic function. Okay, so of course I hope the proof is clear now, complete and clear.
Yes, sir.
Yeah. Okay, so what we have done effectively, of course, we had recalled this theorem, which I had in fact stated at the time of proving holomorphicity of the logarithm. At that time itself, we had seen this theorem. But to apply this theorem, I really needed to show that the derivative is non-vanishing. Of course, continuity of the inverse was already guaranteed by open mapping theorem. All I effectively what I needed is to show that the derivative is non-vanishing. Okay, so it was really important that we have this injectivity, and that was good enough. Okay, so anyway, here I should also mention that in case I was telling you that for R, the moment you have non-vanishing of derivative, you also get injectivity by mean value theorem. So here in complex, also in case of complex also, like you can show that non-zero derivative will imply locally injective thing, but the proof will not be very simple. It will not be as simple as using MBT. Okay, and of course you can only get local injectivity, but nevertheless, like one needs to do some effort, like put some effort. So therefore I stated this inverse function theorem in the form where I take the function to be injected. Okay, so of course if I already assume that the function does not vanish and the derivative does not vanish, then already this theorem itself is going to give you the inverse, so there is effectively nothing to be done. But you can see that in case of the complex inverse function theorem actually work with the assumption that the function is injective. So that's good enough. Okay, great. So we are done with this inverse function theorem, and effectively that's a very, as I said, is a very nice application of open mapping theorem that we have proved. Okay, so what we have seen is that if I take a non-constant holomorphic function, it's going to take open set to open set, and if it is injective, then that holomorphic function is even invertible. Okay, so what we are going to do now, we are going to look at a very particular case. Okay, so namely, we are going to take open set. For example, we are going to take the open unit disk. Okay, and moreover I want to take functions which can be inverted on open unit disk, and also I want to take in such a way that the functions are invertible, and like where my uh, the inverse also has domain as the open unit disk. Okay, so what did we notice? We noticed that non-constant um, holomorphic function, this takes open sets, gets mapped to open sets, and moreover if I have invertible injective one, so injective holomorphic map, then I even get that the map is injective, sorry, invertible. The map is invertible. So therefore I have an inverse which is on the other direction. So now what I want to do, I want to or we now closely look at a special case. What is the special case? Special case is I am going to take my open domain to be open unit disk. Not only that, I also would like to take those functions. So the inverse is also in the open unit disk. So that means, namely, biholomorphic functions on B01. So on open unit disk, I'm going to look at biholomorphic functions. Okay, so that means I have a non-constant injective holomorphic map on B01, taking values also in B01. Okay, so I want to look at such kind of functions. Is it clear what I want to do?
Yes, sir.
Yeah, so here my range, of course, it's going to like we are always taking open domain. So I want to specify my domain to be B01. And also like, of course, I know that once I take injective maps, it's going to be invertible, and I prefer that the inverse is also from open B01. So that means I want to take this by like holomorphic maps, injective holomorphic maps on B01, and since it will be invertible, so it will also have an inverse. So those maps are called biholomorphic functions. Okay, because F is holomorphic, its inverse is also holomorphic, and both of them are on the same set B01. So I want to take these kind of functions. Okay, so I want to really understand what kind of functions can I get as biholomorphic functions on B01. So for this, I'm going to state something called a very important statement in complex analysis, which is called Schwarz lemma. Okay, so let us see what is Schwarz lemma. So let f from B01 to B01 be a holomorphic function. B01 to B01 be a holomorphic function such that f of 0 is 0. Okay, so of course, I really needed to assume this because I am taking a means my main intention is eventually take a function which is going to be biholomorphic from B01 to B01. So therefore, like it's a bijective map from B01 to B01. So therefore, I would of course 0 will have a p-image. So at this moment I am just setting that, let us say 0 goes to 0. Okay, so let us set it like this, means which could be one of the natural condition. And then what can I notice about this kind of functions? We can note the following. So then I have even that mod of f of z is less than or equal to mod z. That's number one. Okay, so for example, if you think of the function f from b01 to b01 to be, let's say, just some z, okay, or some constant times z, where the constant is having modulus less than one or less than or equal to one. So if I take these kind of functions, then I can have, so like these are the kind of candidates one would assume. So you will have mod of f of z is less than or equal to mod z for all z in b01. That's and f prime at 0 will be in absolute value less than or equal to 1. So I was telling you that functions of the form like, let's say, f of z equal to some constant times z. So if you take the derivative of such functions, then the derivative is just that particular constant. And I told you already that we need to take that the derivative, that constant needs to have modulus less than or equal to 1. Okay, so therefore, I have this derivative in absolute value is less than or equal to 1. Okay, so therefore, if I have a holomorphic function from b01 to b01 with the property that it is at 0, the value is 0, then the absolute value of f of z is going to be less than or equal to mod of z, and uh, mod the absolute value of the derivative of f at 0 is going to be less than or equal to 0. Okay, now from the statement itself you can imagine that this mod of f of z, like mod of z, this is kind of maximum on the boundary, which is going to be equal to 1. So somehow this whole thing is going to involve maximum modulus principle. Okay, and if you intuitively, if you think it in that way, then you are not too far. So indeed, that's the case. This Schwarz lemma is going to come from maximum modulus principle. Okay, so this is the first statement in Schwarz lemma, but we can also do a little bit better. I was telling you about the example to keep it in mind that f of z equal to some constant times z. And now what you can see is that under certain additional assumption, you will be able to prove that these are the only possible functions. So what are those assumptions? So further, if either your derivative is in absolute value is equal to 1, or mod of f of z is equal to mod z for some z in b01 minus 0. Of course, at 0 the modulus is same, at 0 the functional value is 0, so it does not really matter. So if I have at least one of these two conditions satisfying, mod of f of 0 is equal to 1, or mod of f of z is equal to mod of f of z is equal to mod z for some z. Okay, I'm not even asking for more than one. Okay, so at least at some point, if I have equality, like the equality of the absolute value, then what we will get, then there exists is constant or a complex number c such that mod of c is equal to 1 and f of z is equal to constant times z. Okay, so what I'm trying to say is that, you see, really I was trying to tell you that you can keep these kind of examples in mind, that f of z is equal to some constant times z. If that's the case, then indeed, if like those are going to be the only possible examples, provided you have an additional condition is either this guy is equal, like mod of f prime at 0 is equal to 1, or mod of f of z is equal to mod z. If we have at least one of these two, and this one is only, let's say, for 1 point, that is good enough, then we are going to get exactly these kind of functions. Okay, so of course you can think of fz equal to, let's say, fz equal to z square. Okay, so that is also fz equal to z square also you can assume, but those functions, for that function anyway, you will first of all not have that the derivative at 0 will not have absolute value equal to 1, neither you will have that mod of f of z is equal to mod z. That will also not be true. So clearly the functions like z square or z cube, those things will not qualify. Okay, and as I told you, the eventual aim is to study functions which are biholomorphic, and clearly functions like z square or z cube, these are not going to be invertible, right? So these are not injective functions. So anyway, we will not be much interested about them. Okay. So of course they satisfy the first condition, of course, but we will be more interested about the second ones. Okay, because you see the second part of the Schwartz lemma in fact is giving some kind of a characterization of our functions. So indeed that these constant times z, these are the only possible choices of the functions. Okay, great. So is the statement clear for Schwartz lemma? Yeah, it's clear. Okay, so like I said, the proof is not going to be difficult at all, and it's just going to be, very simple, and the kind of trick that we have done so many times before. I'm going to use that only. Okay, so I'm going to define a new function. Define g of z as f of z divided by z for z not equal to 0, and f prime at 0 for z equal to 0. Okay, so of course you can write f of z upon z as f of z minus f of 0 divided by z minus 0. Okay, because anyway f of 0 is 0, so you can write like this. So therefore what we know is that we know this function g is
Holomorphic.
very good. This function is g is holomorphic on b01. Because here, as I said, this f of z upon z, you can just treat it as f of z minus f of 0 divided by z minus 0. But anyways, f0 is 0 already given, so it doesn't matter. you can just put f of z upon z. So this g is a holomorphic function. Very nice. Now let us take mod of so now if I take if let's say z some r which is between 0 and 1, then for you know um, any z in b01, we such that mod z is equal to r. If I take any such point, then what do I see? Then what is mod of g of z? Mod of g of z is less than or equal to, so of course clearly here r is positive, so the functional value is fz divided by z. So this is mod of fz divided by mod z, and which is less than or equal to 1 over r, as I know that mod of f of z is less than or equal to 1, because I know that the function is going from b01 to b01. So I always know that mod of f of z is anyway less than or equal to r. Okay, so here what do I see? I see that if I take the circle of radius r, then on that circle the absolute value of g is less than or equal to 1 over r. Okay, so this is what I can see. So that means what? It tells me that for example, if I take the whole ball, so um, by corollary of max mod principle, we get mod of gz is less than or equal to 1 over r for all z in b, let's say closed 0 r. All of you agree to this? For
Yes.
any 0 less than r less than 1. Okay, so because on the boundary of this ball b0r, I see that the absolute value is less than or equal to 1 over r. So max mod principle will tell me that of course if you take the whole ball close b0r, you are not going to get anything different. So that's going to be your upper bound. Now this is true for any a, any r between 0 and 1. So if I let's say tend r to 1 from the below, so if I tend r to 1 minus, then what do I get? I get that, so let me r tending to 1 minus, we get mod of gz is less than or equal to 1 for all z in b01. Is it clear to all of you?
Yes, sir.
Yeah, so I can take r very close to 1, and I'm going to get that mod of gz is less than or equal to 1 minus for 1, mod of gz is less than or equal to 1 for all z in b01. Okay, so once I have this, that means this bound is applicable at the point 0 as well as the points which are not equal to 0. So if I apply it for the point 0, this implies, and 0 g of 0 is f prime of 0, so this is less than or equal to 1, and at other points the value is f of z divided by z, so that implies mod of f of z is less than or equal to mod z. Fine, is this clear to all of you now? For all z in b01, is it clear?
The first one, f prime of 0 less than 1 कहाँ सा है?
Yeah, that is because g of 0 is f prime of 0, right? Now, this inequality
Yes,
is
sir.
valid across the ball. So at the 0, at the
Yes.
point 0 also it will be true. Yeah,
Yes.
so I get these two inequalities. Okay, so now again, I have to consider the case when I said, so this completes the first part of Schwartz lemma. But as I said, we will be more interested about the next part. So next part is telling me what? Next part is telling me that if I get equality at one of these two places, then what is going to happen? Now, if that is the case, remember what I am going to get. If I get equality either here or either here, at least one of the places, what I am going to get, I am getting that mod of gz is, you know, taking the value 1 either at the center or somewhere inside the disk, and where I know 1 is the bound on whole of the ball. And that means what we have seen by maximum modulus principle, the absolute maximum of the absolute value cannot be attained inside the ball unless my function is a constant function. Okay, so let's now apply that. So this completes the first part. Okay, so this is first part is done here. So for the second part, note that if mod of f prime of 0 is equal to 1, or mod of f of z is equal to mod z for some, even 1 z is good enough, for some z in b01, then we get g of z is equal to 1 for some z in b01. Do you all agree to this? Yeah.
Yes, sir.
So either in the first case, that is f prime of 0 absolute value is equal to 1, that means g of 0 absolute value is equal to 1. And if it happens in the other case also, then that particular point will give you the absolute value is equal to 1. But we know mod of gz is less than or equal to 1 for all z in b01. So therefore, what do I see? I see z is a point in the interior where the absolute value is attained. Hence, by maximum modulus principle, what do
G
I
is
get?
constant. G is constant.
Maximum modulus principle. We get g is constant. So say g of z is equal to c. Now g of z equal to c, what will be the absolute value of this constant?
Less than equal to 1.
No, it has to be equal to 1 because I know that at some point, so let us say for some z naught, let me write it
Yeah.
z. So at this z naught, so I know that the absolute value is going to be equal to 1. So clearly mod c is equal to 1 as uh, yes, this. Okay, so you understand why it is true. Okay, anyway, so clearly mod c is equal to 1 and g of z is equal to c. This implies f of z is equal to c times z for all z not equal to 0 in b01, and of course that satisfies this equality is also true for z equal to 0, so I can write this is true for all z in b01. Clearly, is it clear?
Yes.
Yes, and okay, so therefore we see that like this Schwartz lemma gives you that the moment you have a function, holomorphic functions from b01 to b01, which is taking the value 0 and 0, then the absolute value of f mod of f of z is going to be less than or equal to mod of z. Moreover, and the derivative at 0 is going to have a modulus less than or equal to 1. And if you get equality at least in one of the places, then you will get that your function is nothing but constant times the function z. Okay. So of course here I have taken a function which is vanishing like which is taking the value 0 at the point 0. But of course if I just want to imagine function which is like or by holomorphic functions on z on this open ball b01, then I could as well have this 0 at some other point also, right? There is no reason why I should only have 0 at 0. Okay, so I could have 0 at several other points. So let's say I could have 0 at, let's say, some point at a where a mod of a is less than 1. Okay, so we need to take care of all this. So that is why I'm going to, introduce a new function, or like a class of functions, which is going to, be satisfying these kind of properties. And effectively we are going to see that all our biholomorphic functions are going to be given by those kind of functions only. Okay, and clearly that's going to extend the definition of this, or like this constant times z functions. So we are now going to start looking at a particular family of functions which will generalize these f of z equal to constant times z. So let a belongs to C be such that mod of a is less than 1. Okay, so that's the function I want to take. And now you see, as I said, what I want to take a function which vanishes at a. Okay, so give me one function which vanishes at a. Very natural one. What will be a function which vanishes at a?
Z minus a.
Z minus A.
Very good. Now you see what happens with this z minus a. So I was previously, I said that I would like to have my unit ball going to unit ball, but z minus a is kind of giving a translation, right? So the unit ball no longer gets mapped to unit ball, correct? Yes,
Yes,
if
sir.
the map z going to z minus a, the unit ball does not get mapped to unit ball. It gets translated little bit. So I need to, have I need to have some extra factor so that this translation is taken care of. So what do I do? So consider the function. Consider the function exactly like you said. So I am denoting it as phi of a. So phi of a at z is z minus a divided by 1 minus a bar z. So this is the function which I take. So z minus a is to ensure that my function vanishes at a, and you will soon see that this denominator that I have put, this is to ensure that my function, gets the unit ball, it gets mapped to unit ball only. Okay, so this is what we are going to see. Now, here, of course, you can clearly see one thing, that the denominator that I have introduced over here, that denominator vanishes at which point? Tell me, where does the denominator vanish?
1 by A bar.
So if mod of a is less than 1, then what can I say about mod of 1 by a bar?
Greater than 1.
Greater than 1. Very good. So therefore, you see, as far as holomorphicity is concerned, this function, like of course, denominator has a 0 at some place, but this 0 is outside the even the closed unit disk. Correct? Yeah. So therefore, this function, all of you will agree that this function is actually a holomorphic function even on the closed unit disk.
Yes, sir.
You do this. Yeah, so this phi of a clearly as mod of 1 over a bar is bigger than 1, we get phi a is holomorphic on b even closed 0 1. Okay, so that means in an open set containing this closed ball. Okay, and of course phi a vanishes at a only, this you have seen. So phi a vanishes at A only. So this you have seen. And now you can also notice that this phi is actually has an inverse. So this I am not going to check, but you can check that phi A composed phi minus A is going to be the identity. That means Z going to Z, and phi, which is same as phi minus A composed phi. Okay. So this phi actually is an injective function on the unit disk, Okay, so of course, if mod of a is less than 1, mod of minus a is also less than 1. So you can also consider this phi minus a, and it turns out that they are inverse to each other. Okay, so next thing I need to show that, as I said, we really need to show that the open ball, open B01, is going to open B01. So that was the part which I did not check so far, but we are going to do it now. Okay, so let us see. So I want to say that phi A maps open B01 to open B01. Okay, so that is what I want to do. So instead of doing that, of course, we know that phi a is a function which is holomorphic even on the closed unit disk. So what I am going to do is that I am going to show that the closed, clearly you can see that the point A is going to 0. And what I am going to show is that the boundary is going to the boundary. Okay, so therefore inside the absolute value has to be less than or equal to 1, and of course it cannot be equal to 1, by maximum modulus principle, because the function is non-constant. Okay, so that will be the argument to show that phi a is indeed mapping my open unit disk to open unit disk. Okay, so to show phi a maps b01 to b01, we calculate mod of phi a of z for mod z equal to 1. Okay, so what is this? So this quantity is, therefore I can write this is z minus a divided by 1 minus a bar z. So I write it as e power I theta minus a divided by 1 minus a bar e power I theta, because I am taking mod z to be equal to 1. So therefore I am writing z as e power I theta for some theta between 0 and 2 pi, or whatever you wish. So this one looks like e power I theta minus a, and here what I can write, I can take out 1 e power I theta. So this becomes e power minus I theta minus a bar in absolute value. Okay. And if you look at carefully, the numerator and the denominator, they're related, in the sense if you call the numerator to be alpha, then the denominator is nothing but alpha bar. Is it clear?
Yes. Yes.
So this is like numerator is just the conjugate, complex conjugate of the denominator. So therefore this ratio has of course absolute value 1, and clearly none of them are equal to 0, because mod of a is strictly less than 1. Okay, so they are not non-zero, and they are absolute value, like they are conjugate to each other. So therefore this quantity has absolute value 1. So this implies what, mod of phi of z is equal to 1 for mod z equal to 1. So this implies um, phi a of z is less than or equal to 1 for mod z less than or equal to 1, and that's by max mod principle, or rather this is by corollary. It's a corollary of max mod principle, and that implies mod of phi a of z is strictly less than 1 for mod z strictly less than 1 by max mod principle. This is, I think, statement 2. If you take statement 2, you will get this, because phi a is non-constant, as phi a is non-constant. Okay, so that you can clearly see. So therefore what I get is that even uh, this phi a maps unit circle to unit circle, and what moreover we have is that this is taking 0 at a, this phi a is inverse to each other, and all of that. Okay, so we get this one. Okay, so is this clear, all this discussion about this phi a map?
Yes, sir.
Okay, so now just notice a few more things. So if we consider the derivative, then I can say something about the derivative also here. So for example, if you take the derivative of a at the point z, so this is going to be, you know how to, like, this is just product, so you can take the derivative easily. So this is going to be a bar z minus a divided by 1 minus a bar z square. Okay, so therefore I get that phi a prime at 0 is 1 minus mod a square, and phi a prime at a is going to be 1 minus 1 by 1 minus mod a square. Okay, so the derivative at 0 and the derivative at a, they are reciprocal to each other. Okay, so of course, phi a prime at 0 is less than 1 because mod a is strictly less than 1. So this quantity is going to be positive but less than 1, and this quantity is therefore is going to be bigger than 1. Anyway, so this is what we have about phi, the function phi. And whatever we have discussed so far, if I try to summarize, I can write the following proposition. So for a in C such that mod a is less than 1, phi a is a map from b01 to b01, is a holomorphic function, of course, holomorphic function such that this phi a at a is equal to 0. Clearly phi a is injective because we have already seen its inverse with phi minus a as its inverse. Further, phi a maps the boundary to the boundary, so the maps unit circle to unit circle. Okay, so and of course the derivative, so with, I can also say phi a prime at 0 is 1 minus mod a square, and phi a prime at a is 1 by 1 minus mod a square. So all this what we get. Okay, so except for this derivative conditions, for example, so remark, so this width I am putting it in bracket because that is particularly for this function. If I change it by a constant, these values will change. So remark is clearly for any other complex number. If I take any other complex number whose absolute value is equal to 1, then the function c times phi a has the above properties. So the same properties will hold for c times phi a also, because that's just a constant multiple, except for, as I said, this derivative value of the derivative will accordingly change. There will be a multiple of c at each place. So that's why I wrote it in brackets. But in general, this is what we can get. Okay, so now that I understand how, like, this function phi a, what it does and how it maps and all that, so we now have the, so I will not have time to prove the theorem, but I will prove it in the next class. We now have the following characterization, the following characterization. So what is this characterization? Let us see. So that's our theorem, which we will prove in the next class. It says that if I take, so let f from b01 to b01 be any, be a bijective holomorphic, yeah, bijective map, which is holomorphic on b01. Suppose f of a equal to 0 for some, of course it's a bijective map So there will be a point where the function is going to vanish for some a in B01, then there exists c in C such that mod of C is equal to 1 and f is equal to C times phi. Okay, so it turns out that all bijective holomorphic maps on B01 are exactly of the form phi of A. Okay, so of course with a constant multiple, but that does not really matter much. But this is the characterization theorem that we are going to prove. Then of course we have seen various properties of our function. We are going to use them, and eventually we are going to show that our function is going to like if I take any bijective holomorphic function on B01 to B01, so that means any biholomorphic function on the open unit disk looks like C times phi A. Okay, so this is the characterization that we are going to have. So we will see the proof in the next class, and I'll stop here today. Okay, so tell me if there are any questions. I stop sharing. Are there any questions?
So, there is any where to find the maximum and minimum, like we are in a multiple variable calculus.
Sorry.